In today's world, a small MP3 player can store up to 10,000 songs corresponding to 10 gigabytes. These songs are stored in a flash memory as a chain of elementary bricks called bits, corresponding to either 1 or 0. To store one single song using the technology of the hard disk drive from 1954, we would need 1 meter squared. To store the 10,000 songs from today's MP3 player, we would need 500 CDs in 1990s technology or 1.5 football fields using the hard disk drive technology of the 1950s. Instead of increasing the size of memory to store more information, the solution has been to reduce the size of the elementary bits. Nevertheless, bit size is reaching a physical limit. Mass storage is dominated by two technologies: flash memories and hard disk drives. Hard disk drive are high capacity but fragile and energy inefficient. Flash are compact, robust, but low density. Hence, our goal is to develop a fast and energy-efficient memory that is robust and compact like a flash memory, but also dense like a hard disk drive. This technology would help build an eco-friendly, sound, and sustainable IT world. Our investigations are based on hard disk drive technology, but instead of rotating the disks to write and read magnetic bits with a flying head, our novel approach is to make the bits move. This is a solid-state hard disk drive, in other words, a hard disk drive with no mechanical parts. This paradigm shift in mass storage design was introduced by IBM using an in-plane magnetic anisotropy. It is called the standalone storage track memory. This concept stores information in magnetic domains which are up and down magnetic bits. The region between each domain is called a domain wall. By applying a current, a pressure is placed on all the domain walls, resulting in a synchronous displacement of all the domains. Such moving bits can thus be read or written by a fixed head. Let's consider that each domain is like a boat traveling in a canal. If one of the boats bumps into a defect, the sequence of boats, or in the case of a memory, the domains, is altered, erasing magnetic bits. Overcoming this severe limitation, among others, would represent a significant breakthrough for this concept to be taken to an industrial environment. Thanks to the European Commission, our project called MagWire, which includes 3 well-known academic groups and 2 major companies from across Europe, will be able to address these issues. MagWire's final objective is to develop a 45 nanometer node prototype on a 300 nanometer wafer using magnetic materials with a perpendicular anisotropy. Co-funded by the 7th Framework Program, experiments and demonstrations can be made under the best possible conditions, that is, in the outstanding, distinguished, and state-of-the-art facilities at the University of Paris South in Orsay, the U.S. company Micron and the Italian CNR both in Milan, the German company Singulus in Frankfurt, the École Polytechnique Fédérale de Lausanne, and finally the University of Cambridge.